Hello students, welcome back to another lecture on classical mechanics, and today we are going to study the angular momentum of a rigid body. But before that, as usual, we will just discuss what happened in the last class, because those equations are going to be used for the today's work. And therefore, quickly we will see in a few minutes what is the major conclusion that was drawn in the last class work. That is what I have written here, last class work. And then the terminology and exactly the meaning of the diagram is very important. And therefore, I am explaining now once again. Only by looking at the diagram, you cannot say what is the meaning of the diagram. So it requires explanation. So that is why I am also doing the explanation. So if you are also able to follow quickly, in this short time, you can understand what happened in the last class. So you have two coordinate systems which are represented by the capital X, capital Y, and capital Z. So that is one coordinate system. Of course, all the coordinate systems are orthogonal coordinate systems. So you have one coordinate system which is not going to move, which is also not going to rotate. So that is a capital X. That is why I used to say capital letter. Okay, the one generally written down in capital letters, or the one which are not going to move, which are not going to rotate. We say that such frames are stationary frames of reference. Okay, that's a general convention. Then I have drawn another coordinate system in the green color, and the labeling is by the small letters X, Y, and Z. And you can see what is the relation between the capital X, capital Y, capital Z with the small x, small y, and small z. And the relation is quite visible from the diagram. What is visible is that the small coordinate system, that is the green colored coordinate system, is rotated. Okay, is rotated with reference to the capital X axis. There is some small rotation is there. So which means that it is continuously rotating. It's continuously rotating. Okay, and this photo or this diagram represents an instantaneous photograph of the rotating coordinate system. So what is rotating should be clear. The green color, three axes are there, right? That green color coordinate system, X, this one, Y, that, and Z. So that is rotating by keeping this particular axis is the axis of rotation. So whenever something has to rotate, you need a point of rotation that is about the point. So about the point is the origin. This is the origin. So about the point, at the same time, you also require an axis of rotation. So that will be the axis of rotation. And then the direction of rotation is also shown here. Okay, once all these things are shown, you can apply the screw. You take a screw and rotate along the this kind of a direction that is shown. If you rotate the screw like that, then how the thread will move forward, okay, how the tip of the screw will move forward, that will be the vector omega. That will be the vector omega. So the diagram gives a lot of information like this. You have a stationary frame of reference that doesn't move, that doesn't rotate. It is fixed once for all. And then you have the green color coordinate system that keeps rotating at a angular velocity omega. Okay, this is all about the coordinate system. The interesting point and important point about the two coordinate system is that their origins are coinciding. You see this? The origins are coinciding. This is very important. If the origins are not coinciding, that means if one fellow is staying 2 meters away from the rotating coordinate system, then the calculation will be somewhat more difficult and some additional terms will come. So the point to be noted is that the capital XYZ and the small XYZ coordinated system should not be separated farther away. They have to be coinciding. Coinciding means the origin will be always coinciding. Okay, only the axis XYZ will be away from each other because of the continuous rotation of the green color coordinate system. So this is all about the coordinate system. Okay, this is completely mathematics. What is the physics that is going to happen is you have some rigid body. Okay, rigid body could be an aeroplane, for example, or any other object that you like. Okay, you have an aeroplane, and then you are now concentrating a particular point inside the aeroplane. Consider that it is a solid body, and then you touch the airplane and then show that is the R vector. Okay, you can touch any part of the airplane and say that whatever that part I am touching, that is the point R. That's all about it. So you draw the line from the origin of the coordinate system to the point in the rigid body. So what is this last tip here? That is a point in the rigid body. That's a point to be noted. And now what happens is that two things are happening. One is that the green color coordinate system is rotating at an angular velocity capital omega. And then the aeroplane, we do not know what the aeroplane is doing. Aeroplane may be rotating, I don't know. It may be taking a turn and then making a rotation. That is possible. It can also make some kind of a spinning thing. That is also possible. So we don't know what the airplane is doing actually. So in any case, we are going to observe what is happening to the airplane. So that is the meaning of writing down R here. So mathematically speaking, R is any point. Okay, it could be airplane or anything else. So we say that a rigid body, that's all about it. So any point on the rigid body is represented by the R vector, and I want to show it completely different, so that I have written in the, or I am showing in the red color. So the red color object is the one that is pointing to the physical object. The green color and the white color axis are completely mathematical. And there are two observers in this situation. That's very important. Where are the two observers? Both the observers are sitting in the center. That means the origin. One fellow is sitting in the capital XYZ. So you have a chair in the capital XYZ and there he is sitting, which means he is observing. Sitting means he is observing what is happening to the rigid body like airplane. And similarly, there is another fellow who is sitting in the small XYZ, green color. He is sitting in the green color chair, which is also located at the origin. Okay, so then these two people are observing what is happening to the rigid body, which is the R vector. And ultimately what we have done in the last class is, if this is the situation, okay, this is a scenario, this is how the scenario is there, we are interested in knowing what could be the time derivative of the R vector. Time derivative of R vector means what happens if the aeroplane moves, what happens if the aeroplane rotates, whatever it is. Some dynamics is going on to the rigid body. So we would like to know the temporal evolution of that R vector or the position vector. Okay, that gives you, of course, the velocity and other calculation you can do. So the elementary or the very most fundamental, elementary by that it means fundamental actually. By elementary doesn't mean quite simple also. Could be little complicated, so fundamental would be a better term. So the fundamental point that we were interested in doing the calculation is that we were interested to do the time derivative of the position vector R. That's what we have done, and then we got the answer here, or the result that we have it like this. Because keeping the result and then writing down the equation, that is not important. You should know for what configuration you are writing the equation. If you don't know what coordinate system I am using, if I don't know who is rotating, who is stationary, if I don't know anything, simply writing down this equation that you have, equation number 5, then it is completely meaningless. And you can't apply also. Okay, yeah, by knowing this equation, what is the use? You can't solve a problem. If you are getting some problem in GATE or CSIR exam, without understanding the equation, you can't attempt to solve the problem. So that's what I mean to say. So now that you have seen the coordinate systems and then you know what is the actual scenario, the understanding is very easy. The understanding is this one. The observer who is sitting in the stationary frame of reference, that is what is the meaning. The observer sitting in the stationary frame of the reference will write down in his note the value of the dr by dt will be equal to capital omega cross R plus, capital omega is, you already know what it is. Okay, that is the quantity. Then plus the value written by the fellow who is sitting in the green color coordinate system. So this means the first information has to be written down by the fellow who is in the green color coordinate system, dr by dt. So which means that essentially it is like this. So two people are sitting in two coordinate system, means the fellow in the stationary coordinate system, he will call the fellow who is sitting in the green coordinate system and ask him, what is your observation? Like that he will ask him. Then this fellow in the green color coordinate system will reply that I got dr by dt in my R. That is his answer. Dr by dt, putting the suffix R means what? He says this is my answer. So he gives a reply saying that my observation is dr by dt with R. That expression he will give, whatever it is, number. Then this fellow will write, that means the fellow in the stationary frame will write that this is equal to capital omega cross R plus the green fellow's answer. You got it? That is the meaning of that. So if the fellow who is sitting in the green color answer says that there is no change for me, 0 is my answer, if he says, then okay, then it is 0 plus that. Is that point clear? So now you see, after understanding this, you come and see the another equation, that in many of these simple situations, the observation given by the green color observer will be 0. Okay, so in such a situations, we can quickly write down that dr by dt is actually omega cross r, where the omega is written down as the angular velocity of the rigid body itself. So this is the place we'll have to see that usually the capital omega is usually capital omega means we attach to the angular velocity of the coordinate system. If it is a small letter, lowercase letter omega means generally it refers to the angular velocity of the rigid body. This is the general convention, but in question paper, for the purpose of confusion, they will change it. So you have to be careful about that. But generally, small omega means for rigid body, capital omega means for the coordinate system. So this is the main conclusion that we have, and therefore you should know whether to use the equation number 5 or the simplified version. What is that you want to use? That depends on the statement of the problem, in the question paper. So meaning is very important, only then you can understand. So now we are going to a scenario where we will be using this simplified version for the calculation of the angular momentum. So therefore remember this equation, dr by dt, remember that this is velocity. Probably I will write down here, and I will write down why this is important. Then it will be easy for you to realize what we are planning to do. The idea is like this. This dr by dt is nothing but velocity, so isn't it? So therefore I can write down this is velocity, and therefore that will be equal to omega cross r. So this is fine. So now what is the today's plan? Now today's plan is that we are interested to calculate the angular momentum, and you know the standard formula, namely that you can take the moment of the linear momentum. Okay, so that will give you. So then what you do is this r cross, this can be written down as m into v for the linear momentum, and generally for situations with the mass being constant, for such situations we can write down that this is r cross this particular v. So now you have to see that this particular v is this one. So this is the place where we are going to use this and substitute an omega cross r here. So you can now understand where this expression is entering into picture. So ultimately we say that this is the angular momentum, and that's all about it. So the connection to the calculation of the angular momentum to the yesterday's class should be clear. So this is the point where I would like to emphasize the connectivity between the yesterday's class and today's work. So let us therefore exactly move on to the today's class work, and then I will draw a diagram corresponding to the rigid body, and then we will see how to write down the expression for the angular momentum. Okay, so I'll go to another board for the today's class work. Okay, so this is the today's lecture on the calculation of the angular momentum, and angular momentum is connected to the moment of inertia. So as we go along, we will see what is the detail. For the time being, I will finish the drawing of the axis or the coordinate system corresponding to the rigid body that I have drawn, and then we will give some kind of a label xyz and then the origin. The point to be noted is that this is an orthogonal coordinate system. So that point should be clear, and for the purpose of clarity, I will show some kind of symbolic representation for the 90-degree angle. Okay, otherwise, this is in 3 dimensions, so sometimes you think that it is not 90 degree. So just for that clarity, I'll write down that this is orthogonal coordinate systems we are using. And once these things are clear, we will choose any point in the rigid body as usual, and then show that is an r vector. I'll show that now. So any point on the rigid body, let us represent it by some kind of a symbol xyz as a representative, okay, and then say that the r vector. So the r vector meaning is quite clear to you. It is as simple as what you learned in all the way from school. I am planning to write down that any point on the rigid body is represented by the symbol r vector, and r vector is the very standard notation that it is equal to some xi plus yj plus z times k. That's what I'm writing, and therefore what happens is that now that the rigid body is rotating about the origin O, so I'll write down that also the rigid body is rotating, it's going to rotate about the origin O. So origin is important, and we need to specify the point of rotation, that is the about. Okay, we always say that about the point, that is the origin, and then we should also represent where is the axis of rotation. These two things are quite important in the rotation. So I will now try to draw some kind of line and show the axis of rotation in some pink color. I'll take a different color, maybe pink color I will choose, and then I will try to draw. I have to draw properly with a straight line. So sometimes it comes nicely, sometimes it doesn't come. Okay, so this vector is corresponding to the right hand screw rule that you have to apply. Symbolically, we can represent like that. So this is a symbolic representation. That kind of clockwise rotation. That kind of rotation is symbolic, not mathematical. For mathematical representation, you have to go to the screw rule. You have to take a screw and apply, and then that will tell you the exact direction. So once these diagrams are clear, we can then write down the expression for the angular momentum. So what is actually happening in this particular case is that the r vector, what will happen to the r vector? So r vector should be in green color, right? So let me put in green color. So r vector, when this is rotating with respect to the axis of rotation, which is a pink color one, pink color is the axis of rotation. So when that is happening, then what will happen to the green color vector is that it will rotate like that. See, it will rotate something like this. And therefore, how I'm talking about the appearance of the r vector. So the green color r vector will be rotating along some kind of a cone. It appears as if a cone is formed. So that's what I'm trying to write down, that the vector will execute a kind of a cone because of the angular velocity. So these are the geometric constructions for the understanding purpose. And once this is clear, let us write down what is the expression for angular momentum. And we are going to use the standard definition. So I'll write down that it is by definition. Okay, so it's by definition. The angular momentum is given by. That is the standard R cross B formula, which you just know I explained, so it will be comfortable. Which you can simplify it as R cross m times dr by dt. Which is equal to, you simply substitute the omega cross r now. This becomes omega cross r. Now here what is m and other things you'll have to note down. This is general formula, right? Right from the school you have r cross b, but in our diagram what it is, so that point I would like to round. The so-called point that I have shown for the r, no? I am showing an arrow. That one, in reality what is it? It is representing a small mass in the rigid body. A point in the rigid body means what? If you are going to touch an airplane with your finger, then the amount of mass that is confined in that particular region is what we called an elemental mass or a small mass. Because for our calculation we need a small mass dm. The small mass is also called elemental mass. not elementary mass. Okay, it is elemental. Elemental means differential. A differential element, small element, that is called element, not elementary. So that dm is the meaning that is obtained from the position vector. So wherever you are going to put your finger on the rigid body, that could represent a small portion of the rigid body, and we will say that is dm. Even though we have written r cross p and then p is m times dr by dt, now m is going to be replaced by dm. So that is why this clarity will come when I explain like this. And therefore, we will now write down, because of this reason. Now, let us rewrite this expression in the integral form. So the point is clear. The other things are only statements I am writing. Once the mass becomes differential mass, angular momentum becomes differential element, and therefore L has to be integral. That's what I am telling. It's a matter of saying that because of the differential element, we perform an integration. That's all. So I try to write down in a better statements slowly, so that it is also possible to follow easily. And in addition, you can also write down the notes. So for that reason, I am taking some time and writing down all the details. Now I'll write down like this. Since a rigid body is a three-dimensional object, there is a point to be noted here. Rigid body is a three-dimensional object, but how many integrals should be there? This has to be a triple integral. So I'll write down that this has to be a triple integral. But symbolically, one integral is enough. This is a point to be noted. You don't have to show three integrals there. If you want to show, you can show, not a problem. But just by showing a single integral, it's all fine. There is no problem at all. As long as it is representing a three-dimensional vector, the integral naturally represents triple integral. That is the meaning. For clarity, if you want to show three of them, then you show three of them, not a problem. Okay. So now that it has so many cross products are there, let us evaluate the omega cross first. Omega cross R. Afterwards, we will evaluate R cross omega cross R. Because this is a determinant, the other things are simple. So let me write down the expression. It is the standard determinant that you can evaluate. So now there is nothing much to explain. I'll write down the components omega x, omega y, omega z and x, y, z there, and then expand this determinant saying that ax into, you can follow some cursor. Maybe sometimes I'll show that the multiplication and subtraction minus ay into minus x times omega z, close bracket, then you have a plus az unit vector into you have y times omega x minus x times omega y. So one cross product is over. Let us take another cross product, that is cross product of the cross product. So R cross omega cross R. So that we will evaluate. So that will be another determinant actually. Looks a little bigger, but it's okay, not too difficult. The expression may go a little bigger. That's all about it. The bracket is important. So don't forget to put the bracket. The bracket is the one inside, or the omega cross R should be inside bracket. Otherwise, there is a problem. There is no commutative property for cross product. And then, okay, first part is, not omega. I think the first one is R, right? R means x comma y comma z. So let me write down here x comma, then that is y, and that is z. Then omega cross R, you have to go to the previous equation. So this you can't write directly. So let us see that and write down. The first part is z times, so let me write down that z times omega y minus y times omega z. That's the first part. The second part you have to see carefully. There's a minus sign is there. So you have to take the minus sign inside. So I'll take the minus sign inside and then write down that. So it becomes x times omega z, then minus z times omega x. And finally the last term is there, which is You can write down like y times omega x minus x times omega y. And that's all about it. Now we'll have to simplify this. But you'll have to remember that this is only cross product. So I'll write down the note. What is the note is, this is not the angular momentum. Okay, this is only cross product. So the integral is yet to be done. That's what I'm writing. We are yet to evaluate the integral. This is only a triple product. I mean, this is only a cross product. That's what I want to tell you. Okay. So that is information. So I will just separate it. Let us put some line and separate this statement. So that it won't disturb the main track. Okay, so let us expand this determinant now. So expansion will give you that is equal to, we have ax unit vector, open bracket. Now you have to do the cross multiplication. You'll get a y square times omega x minus xy times omega y. And then we have a minus zx times the omega z. Then you have a plus z square times omega x. That's all. Close bracket. Then you have a minus the y component. The y component part is this. Now you'll have to close that and then take a cross multiplication. Xy times omega x. Xy times omega x minus x square times omega y. And then here you will be getting the minus sign, I think. Yeah, minus will come. Minus z square times omega y. And now it is plus zy times omega z. And that's all. Close the bracket. And then we have the last part, az. I think az unit vector should be visible now. So we'll write down plus az unit vector multiplied by, open bracket. Then you have, now it is minus y z times omega y. Now it is plus. So plus, it is y square times omega z. Close bracket. So that's the expression that you have ultimately. And it's all okay. Right hand side you have simplified. But what is the left hand side? You should not forget what is there in the left hand side. So that is actually r cross omega cross r. So it's only a cross product. Okay, we have not finished the evaluation of the angular momentum. By that we have not done the integration. So the point we noted here is that, okay, let us simplify by taking some, if at all, some parts that can be taken common. There is something common, right? Omega x is common. So I'll write down like that. If you take omega x common, I'll put a tick mark. Okay, that one in the last term. What is common? Omega x is common. So if I take omega x, then y square plus z square into omega x. That's the only thing. I think there is nothing is common. So let us copy that. Xy times omega y. Then I have minus, and the last one is zx terms. Zx times omega z, close bracket. This minus we will make it plus now. So I'll put a plus now, because this minus will take inside and then simplify. So then we get a y component. Minus is important. It is going to you have to take it inside like that. And now what are the terms that are there is, so let us write down minus yx times omega x. And now it becomes plus now. Minus of minus is plus. Then it becomes x square plus z square. If I am taking common y, common is omega y. Common is omega y. And that's over. Then you had a minus y z times omega z. And that's all. Close the bracket. Then plus. Once again, I'll write the z component now. And here there is no trouble. Almost it is copying the same expression, but we will try to take the common. That's all about it. First term is over. Second term would be that, and let us write down minus zy omega y, And the last term, now only there is something common. Okay, so you can understand where is the common. So that becomes x square plus y square times omega z. So this particular step is only to take something common. That's all about it. But otherwise, nothing big. Okay, now is the very interesting thing. So I will write down here in a different color. I'll choose yellow color now. The point to be noted is that we have finished the calculation of the cross product, and now we can leave it like this and perform the integration. Okay, that means almost we finished all the simplification over, and now if you perform the integration, our job is over. We got the angular momentum. So that is the point I'm writing. We can leave it like this. Okay, then the right hand side is what is the vector quantity, and the left hand side is also a vector quantity. So I want to emphasize this, isn't it? Left hand side, what is there? You please read now. R cross omega cross R. It's a vector. Everything is a vector. So why do you want tensor? That is a question. So only when something is clear, then only you will understand. Everything is vector. Everything looks good now. Left hand side is vector. Right hand side is vector. Then why people say moment of inertia is a tensor? So that is the question. The answer is we don't want to have such a big expression. So the question is that can we write down an elegant expression? Okay, is it possible to write? That is the first question. If it is not possible, it's a different story. So the question is clear. Can we write down in the more elegant way that particular big expression? So that is a question. The answer is that, okay, if you want a little good looking equation, that's what I mean to say, an elegant appearance, maybe we can try some kind of a matrix form. So let us try how to write in matrix form the above equation. So you'll have to visualize where is matrix possible. Is it possible or not? First of all, you'll have to visualize. So let me go back and then see the entire equation and then try to write down in the matrix form. So open a big bracket, okay, so that you can write some matrix and try to write, and let us see whether it is successful or not. Okay, first component you write down, which is y square plus z square. I'll write down that. Okay, then there is a multiplication omega x is there. No, that you don't worry. That we will write down later. So only the corresponding components you write down minus zx, and so 3 elements are over. Close the bracket. It goes ugly. This is no drawing. The straight line is difficult. Okay. Similarly, write down the second part minus yx. Then you have an x square plus z square. And then the last part is minus yz. So you have to be careful with minus and plus. Okay. And the last term is minus zx. Then you have minus zy. And that one is x square plus y square. And then what are the missing things? You write it as a vector. So open another bracket and say that it is a column vector. Now in that column vector, what are you going to write? You can write down the missing part. What is missing? Omega is missing. So write down omega x. Omega y was missing. Now you write down that. And similarly, the omega z. But now remember, whether they are equal or not is a very important question. Simply you write something and say that is final. No, that is not possible. That is why you have to think carefully. Now you compare whatever we have written with the previous expression. Ask whether the question is correct or not. Okay, so therefore I will write down that for clarity. I will write down as a statement. Okay. The question is this. Okay, we have written, but what is the question is, where are the unit vectors? Where are the unit vectors? Because in the previous expression, you have the ax unit vector, ay unit vector. Where are they? Totally missing. No unit vectors are there. So your matrix representation is something wrong. That is what I want to emphasize. I am highlighting. What I am highlighting is, in the matrix notation, unit vectors have disappeared. Where will you put? Okay, so this point I would like to write down so that you can feel what I am trying to explain to you. If you want the equation to be more elegant, then in the matrix notation, unit vectors can be attached to the diagonal elements only. That's what I am trying to write. Can be the unit vectors can be attached to only the diagonal terms. Those things will come only if you see the unit vector and search where are they. Unit vectors cannot be attached to all the terms. Okay, but what about the cross terms? You know what is diagonal and cross term, right? In a matrix, diagonal term, you know cross term. Cross term means all other off diagonal terms. So this is an example. That green color I'm making circle, right? That is an example of off diagonal term. Off diagonal term means cross terms, for example. So for all these terms, we are unable to attach the unit vector. In the matrix notation, I am talking about in the matrix vector notation. So what happens is these cross terms we are unable to attach the unit vector if you want to express in the matrix vector multiplication. And diagonal term I will also show you for clarity, in some kind of highlighting. You go in the diagonal direction. Okay, green color is not good. Take another color. So that is the diagonal element. The diagonal elements, 3 elements are there, right? Probably we can attach a unit vector if you want. That is possible. Okay. But if you attach that, then what about the other terms? So that is a difficulty. So you will have to realize the difficulty. Only then you can understand why tensor is required, first of all. We can't attach a simple direction. A direction means, what do you mean by that? Direction, unit vector. Direction means unit vector. So you are now in some kind of a situation where a difficulty in expressing in unit vector is difficult, and therefore you are in kind of a situation where you have to discover a new mathematical entity. A new mathematical entity. Entity means some object. That quantity we will call it as a tensor. That's what I'm writing. So the situation is going to demand that we'll have to discover a quantity called tensor. So let me explain what is a tensor in plain language. Let us not worry about the physics now. Let me move on to a different board. I'll go to a different place in the board. Okay, and now what is the plan is that we will try to understand the some concept, okay, using plain English or plain language without any reference to physics. What I'm trying to do is you simply see that some east, west, north, south I have drawn for easy understanding. It is a kind of unit vectors. We are unable to use unit vector, I told, right? But still directions are there. Now you can see that there are so many directions are there, like east, west, etc. But how to fix the unit vectors? In addition to this difficulty, now whatever I am writing in the green color, that is additional direction. NE means northeast. So northwest, NW. Let us write down SW means southwest, and then come to the one more direction is what is left out is the southeast. So let us write down the southeast there. So what do you mean by now? Now you see how many directions are there. If this many number of directions are there, and bringing a kind of unit vector like AX, AY, AZ is not an easy job. Okay, so totally how many are there? Here you have 4. Okay, earlier already 4 are there. That's what I mean to say. So 4 more directions. So the question therefore is very clear that how are you going to deal? So let us take an example. You take a practical example like this. Something like, you consider some kind of an auto driver or a taxi, and you want to travel. Okay, north direction, south direction means some kind of a traveling. Consider you consider a taxi fellow or an auto driver. You want to bargain how much amount of money I have to pay to reach destination. Destination may whatever it is. Okay, 10 kilometers, something like that. You imagine, and the auto driver says like this: if you want to travel in the east direction, pay $20. If you want to travel in the northeast, you have to give me $30 for the same distance. Same distance is important. Same 10 kilometer. $25 in the north. You put some number, okay. And in the northwest direction, he is demanding $10. So this is something completely unexpected, right? Usually you can travel in any direction and pay the same amount of fare. I mean, the fare that you are going to pay. But this particular taxi driver is asking different fare, that is different amount of money, if you want to travel in different direction. So that is a kind of a crazy situation that you'll have to imagine. Okay, so it's a crazy situation in the sense that you first to tell me the direction, then only I will fix the rate for you. Like that he is telling. So this is the scenario that you have to now understand, and we make a conclusion. I'll write down. So what did you understand? Our conclusion is the following. Our conclusion is that the taxi fare is depending on the direction. Is depending on the direction means I will say direction dependent. So the how much amount of money you have to pay, that depends on the direction in which you are going to travel. Such a thing is known as a direction dependent quantity. Directional dependence or direction dependent, okay, whatever be the thing. So let us now come to the physics. Now if you are going to translate this in terms of physical term, and now I will write down that a physical quantity, I'll write down in terms of some physical quantity, a physical quantity that depends on direction, that depends on direction. Such a physical quantity is mathematically known as a tensor. Okay, it's mathematically known as tensor. So mathematicians have given the name tensor to describe such a physical situation. So that kind of connectivity, if you understand, then you can now feel whether tensor is not so difficult, but you can understand and appreciate when tensor will be used. Okay, when tensor will be used, when it will be used means answer is very simple. When it is direction dependent. So that's all fine. Now let us see how it looks like. Let me write down how it looks like. It looks like a single number, 10, 20, 30, single number. Otherwise, it can be a set of numbers in a row, something like a row of vectors. You can write in terms of even column vector. So I'll write down that. A tensor will have the appearance of a column vector. I'm talking about appearance. How the tensor will look like? It can appear like a column vector. That is also possible. Not only that, it can also look like a matrix. So if you know the appearance of tensor, then there is nothing to worry about, because all these things you already know. Okay, not even a simple matrix. Let me go to another situation where you can have multiple matrices. Multiple matrices is called layer of matrix. Okay, I will put layer in layers of matrix. What do you mean by layer is one matrix on top of another matrix on top of another matrix. Like that, if you put one on top of the other, we say that it is layers of matrix. So all these things are tensors. So there is no difficulty for you because you know everything. Column vector you know, matrix you know, multiple matrix you know. So what is there to worry now? So tensor therefore is the generalization of scalars and vectors. So that is how you quickly understand. Okay. So what is a tensor means? It is a generalization of scalar and vector to the where it is a generalization to the higher dimensional mathematical dimension. I'll write down higher mathematical dimensions. So in such a quick time, and you can easily grasp what is the meaning of tensor, why tensor is used first of all, and when it is useful. It is useful whenever you have directional dependence. So I'll therefore write down that in such a scenario, you can't use a unit vector. Let me write down that the unit vectors are not usable in such situations. Okay, because why I'm writing unit vector is our angular momentum, r cross omega cross r, that contain unit vector. So now we are going to throw away the unit vectors and then write them in the form of a matrix. Okay, now you may the connectivity I will write down. What is the connectivity is the directions will be linked to. I will write down directions will be linked to. What do you mean by linked? Means attached. Okay, attached to. Where it is attached to means it is attached to the coordinates used to define the tensor. So there will be a coordinate, then only you can define tensor. So what coordinate are you going to use? That will determine the direction. That will fix the direction. So you don't have to worry even though unit vectors are not there. The coordinate system will take care, and that will specify the direction. For example, it is not that complicated. Things will be simple if I write down an example in 3 dimension. Take in the case of the 3-dimensional example, what will you do for the vector? What will you do for a vector means something that you know already. I will write down x direction, y direction, z direction. I mean x component. Okay, x component, y component, z. So that is known to you. So 3 of them are there. Now in the case of tensor, what will happen? That is a question. So in the tensor, what will happen is it is going to be a similar situation. So I will write down that. I'll say that it is along x direction. It is same thing. I mean, nothing changes. It is very much similar to vector only. Whatever I wrote, along y direction, along z direction. But now comes the but. In addition to these three directions, we can fix many other directions. So that is what I am trying to write down. So I will extend this space. And then in addition to these three, I'll separate them. In addition to these three, we can write along the xy direction, along the xz direction. So you can take the xy, xz means, northeast, northwest, southeast. You now understand what you mean by xy, xz. So these kind of scenarios we can handle. So what are the all possible combination I am writing? Let me finish the all possible combination. Otherwise count will not come correctly. Okay, you have to write down the total count. We need 9 of them. That's why I'm counting. Let us count and see how many are there. Then if 9 of them are coming, then it's fine. Let us count. Okay, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have written all possible. So the entire thing, that gives you this entire thing what it is. This gives you 9 possible directions. So the advantage is that with the tensor you can deal with 9 possible directions. That is what it means to say. And then appearance wise, how this 9 directions will be represented, how to write down those 9 numbers, 9 numbers, how to write. So one of the easiest way to write down the 9 number is by a matrix. You open a matrix and write down 3 by 3 matrix. So let me show some kind of a 3 by 3 matrix like AXX, standard notation. Okay, something like AXX, A is a vector means how will you write? The first one can be written by AXX, second one can be AXY, third one can be AXZ, etc. And this this will be YX, then you have YY, etc. So you fill that. So now you understand how 9 numbers are coming. 9 numbers are coming because of 9 directions, and those 9 numbers can be filled in a form of a matrix. And once it is in the form of matrix, we know how to deal with matrix mathematics we know. So what happens finally is that ultimately what happens is that we come to an agreement or we agree that matrix representation is a good option for you or a good alternative for you in place of unit vector. What I'm trying to say is that in place of what? In place of the vector. So matrix representation is not the only thing. It's one of them, but much simple things are there. You can use a single number, you can use a row of vectors, you can use a column, you can use a single matrix, or you can use multiple matrix. Layer means multiple. Anything you can use, everything, any combination that you are going to write down is a tensor. So our conclusion, therefore, the conclusion is that the representation of the matrix, therefore, is a tensor quantity. I'll write down that this kind of matrix is a tensor. So you don't really worry because of this. So let us go back to the moment of inertia calculation. So we were asking this question, right? What happened to the unit vector? The answer is that okay, let us throw the unit vector and then write down in the form of tensor now. That's all. That is the answer. So that I will write down that recognizing that this particular object is a 3 by 3 matrix. I think 3 by 3. Let us write in white color. It's a 3 by 3 matrix. We will call this matrix as a tensor. It's not something new, right? Same matrix only. We call the same matrix as the tensor. Because of tensor, nothing happened special. It is the same matrix, but we are going to give the name tensor. That's all about it. And the reason is that there is a direction connected with that. That is very important. There is a coordinate system connected with that. That is why tensor can be used. And we can also use the name moment of inertia tensor. Okay, that is only due to physical dimension. In general, it's a tensor. Why you call moment of inertia tensor means it has the dimensions of moment of inertia. That's why. Okay, so once these basics are clear, we can now write down the conclusion. Let us go to Yeah, I want to write conclusion now. So this should not disturb. The angular momentum is given by the triple integral of the mass element multiplied by r cross omega cross r. So that how is it going to look like? It is looking like how it is going to look like it is looking like a matrix, and that matrix we will call as a tensor. So that is an object that you have. Then that object is multiplied by a column vector omega x, omega y, and omega z. That is how the equation is looking like. Okay, so you should have the class notes. So otherwise, I have to go up and down in the screen or the board. That will be difficult. At least you please see whatever I have written, that appearance is there or not. Okay, so if I go up there, the previous one, so you must be able to see whatever I have written here. Only thing is that the integral you have to transfer there. So that is the one I am talking about. You'll have to put the integral there. Okay, so put an integral there. Those integrals will be transferred inside. So put the integral everywhere. That's all about it. But other than that, nothing. You put the triple integral to every element. That means 9 elements of the matrix. That is what I mean to say. And therefore, the moment of inertia tensor is, I will write down that, the moment of inertia tensor will be given by, or it is moment of inertia tensor means moment of inertia matrix. So open a big bracket. So open a big bracket because we are trying to write down the 3 by 3 9 elements, and each element is a triple integral. So let us open a little bigger bracket so to write all the things. First element is as usual y square plus z square. Now the elements, you keep with you in the previous notes and then write down easily. I will not go back and forth in this board. That will be difficult. So the last term would be a minus d, I think x times z, and then you fill it. But only thing is that you be careful to write the integral with a dm, because dm is going to tell you the differential element. Don't forget about that. Every integral dm should be there. And then here you have x square plus z square, then once again dm. So dm should be there everywhere. So I think the previous one, see there also one dm was missing. Also dm, so that dm missing, let me write down that. Okay, and that's all. So the last one is minus zx dm, then the next one will be minus zy dm. The last element is plus integral x square plus y square dm, and all the elements are over. Close the bracket. Okay, so you just make sure that what you have written is correct. Okay, only thing is we have attached integral and dm. There is an integral, there is a dm. Where you have to compare this previous expression. So this expression, we have to put an integral there, and then we have to attach a dm. That's all we have done. We have not done anything else. So that's all. So what is the conclusion is, this is a 3 by 3 matrix. Okay, so it's a matrix, but each matrix element is an integral. So I'll write down that the matrix elements are the integrals. So this is the moment of inertia tensor. When you want to evaluate it for a particular configuration, you have to evaluate 9 integrals. So remember that. So let us come to the answer to the question, why moment of inertia became a tensor? That was a question that we can ask. On what basis moment of inertia has become a tensor? The answer is this. The answer is very simple. Moment of inertia depends on the axis of rotation. Moment of inertia depends on the axis of rotation. That's all. That is the answer. So this is a long, by that I mean to say it's a long answer, because in the beginning I told what is a short answer. Okay. A long answer means we have done all the calculations and then we are showing, but there is one terminology you'll have to be careful. So let me put some terminology in green color. There is a new term actually that is known as the product of inertia. So I'll show that first of all. In green color I'll write down the terms that are off diagonal. Off diagonal means in a matrix off diagonal, like this. This is an example. Off diagonal. This is known as the products of inertia. This is not moment of inertia. So I want to tell you that The terminology is slightly different. Moment of inertia is a diagonal term. You see how many off diagonal terms are there? All these things are off diagonal terms. Okay. And I don't know why this is coming here. Yeah. Okay, these are off diagonal, and this is the diagonal term. Diagonal term is the standard moment of inertia. The standard moment of inertia you already know is the standard term. The additional term that are coming because of the tensor nature is product of inertia. Terminology is slightly different because you don't have squared term. You see x square, y square, z square, those terms are not there. That is why it is called a product of inertia. Okay, so that is the conclusion now, today's work. So with this probably we can stop for this today's class work.